We are actually putting everything together and doing the real electron configurations. So this is just a couple of definition type things. We are only going to be doing ground state electron configurations. We're not going to worry about excited state because it's just at this state it's not necessary. Just like every element had a unique spectrum, that spectrum is caused by its unique electron configuration. 3 rules we have to follow. And the first one is the Aufbau principle, and that says that we're going to fill the lowest energy levels first before we can move on to the next one. So like we'll fill 1s before we move on to 2s. We'll fill 2s before we move on to 2p, and so on and so forth. This up here kind of starts to get a mess because once you get to about the 3rd energy level, they start to overlap and look really weird, and I've got a better picture for it that relates it more to your periodic table a couple slides from now. Other 2 rules, you have the Pauli exclusion principle, which says you can't have 2 electrons in the same place at the same time. And you have Hund's rule that says when you have a sublevel that has multiple orbitals, so these are only sublevels P, D, and F. S doesn't apply with Hund's rule because there's only 1 orbital in an S sublevel. But, you know, P's got 3 orbitals, D has 5, F has 7. Just review your notes from yesterday if you've forgotten that. Each of those orbitals will get 1 electron before anybody can have a second one. And I call this my birthday cake rule, where, you know, if you're at a birthday party, everybody gets 1 piece of cake before anybody can go back and have seconds, or at least that's how it should be. And if you're the one that's hogging the seconds on the birthday cake before someone else has gotten their piece, then you're just being rude. So the 3 rules, Aufbau says lowest energy levels filled first. Pauli says that you can't have 2 electrons in the same place at the same time. This will kind of make more sense once we start talking quantum numbers, in that no 2 electrons can have the same 4 quantum numbers. And like I said, that will make significantly more sense a little bit later. And then Hund's rule says each orbital in a sublevel gets 1 electron before anybody gets a second. I don't like that picture, so I'm just going to skip right over it. 2 ways to write configurations. You have the orbital notation, which is what I have a picture of right here. Each orbital is written as a line. And so like for the S, you would draw your 1s orbital and label it underneath. And then you would, the arrows right here represent electrons. If you had a p, say you had 2p, well then you would draw the 3 blanks because each blank represents an orbital and each p sublevel has 3 orbitals. And then you would label it underneath and you would fill your electrons in. You always draw the up arrow first. So if we were filling in, say, 4 electrons into this 2p sublevel, you'd go up, 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 and then you would do it down, because Hund's rule says each orbital gets 1 electron before anybody gets to double up. And the other way of writing it is the electron configuration notation. I just kind of abbreviate this as EFIG notation. And this is where instead of having the blanks with the arrows, like for this, instead of doing all this mess, you would just simply write 2p4. And the 4 comes from the number of arrows that you have drawn. So this is the picture that I like. It kind of shows you how to read your periodic table when you're filling the sublevels, because the periodic table is nice and neatly organized for you. A couple of things I do want to add to the periodic table that you made in class are that when you're dealing with the transition metals, if you notice, 3D is in row 4. And the reason for that is because the D block, when you're putting in it using the periodic table, the D block is the row number minus 1. And the reason for this is if you go back to that slide a couple slides ago with the weird, wonky slanted lines and stuff, 4S actually has more or less energy than 3D, so you have to fill 4S first, and then you go back to 3D. So the periodic table is written in the order that it needs to be filled. And your periodic table has the F block inserted in. It's the full expanded version. And if you notice, 4F is in row 6. And the reason for that is because the F block is equal to the row minus 2. And if G ever got slammed in here too, it would be row minus 3, and that pattern would keep going. So how do you write a configuration? And this is really specifically for writing an orbital configuration. Because this deals with the blanks. So first you need to find how many electrons in the atom. We're dealing with nothing but neutral atoms, so this is going to be equal to the atomic number. What sublevel is it in? You would just simply say, what energy level, and then is it in the SPD or F block? We'll do some examples of this in a sec. Draw out the lines for each orbital, starting at 1s and ending with the sublevel that you identified up here. And you're going to be drawing a lot of blanks. And then add your arrows until you match up to the atomic number. So for some practice on that, remember you can pause this anytime you want. You can rewind if you need to hear me re-say something or whatever. So I know we did silicon in class, so I'm actually just going to leave this screen blank and we'll just do a bunch of different elements that I just kind of pick at random. So let's have the first one we do can be, how about sodium? So sodium is element number 11, so that means we have 11 electrons, and it is in energy level 3s block, and it is the first element in the 3s block. And so we're going to do both orbital notation and electron configuration notation, and it doesn't matter which one we do first. So I'll start on this one with the orbital notation, and then the next one we do, I'll start with the EFIG notation. So we start at 1s. So each S sublevel gets one blank. So there's 1s, then after 1s is 2s, then after 2s comes 2p. P gets 3 blanks. And then after 2p comes 3s. S's get 1 blank. And since we're now in the sublevel we identified, then we can stop. Now we need to fill in 11 electrons. Now I know that all of my sublevels before my last one are going to be full, so I can go ahead and fill them in. So there's 2. There's 2. Remember, each S sublevel gets 2 electrons. P gets 6. Everybody gets 1 before anybody gets seconds. And then S, in this case, it's 3s1, so we only put 1 electron in that S. If you want to double check it, count them, make sure they add up to 11. So we got 2, 4, 6, 8, 10, 11. Yay! Couple things you can do with this information here. First, you could tell me how many valence electrons there are. And the valence electrons, to find that, you look at the highest S sublevel, which in this case is 3s, and then you check, do you have a matching P? Well, a matching P would be 3p, and we don't have any electrons in 3p, so the valence electrons for sodium is just this one lonely little electron here. And then if I wanted to know how many unpaired electrons sodium has, this will become important later. Just identifying it now is all you need to do. Unpaired would be any up arrow all by itself, so it also has 1 unpaired electron. Now this is the orbital notation. To draw the electron, or to write, I guess, the electron configuration notation, you still read the periodic table, except instead of arrows, you do superscripts. So it would be 1s2, because there's 2 electrons, 2s2, 2 electrons again, 2p, 2, 4, 6, and then 3s1. The way you can get this off the periodic table is just counting the number of squares that you go through to get to sodium. And if you notice, these superscripts all add up to 11. So another example that we can do, let's do, how about some cobalt? So cobalt is element number 27, so we have 27 electrons, and it is in the D block, row 4, but remember D is row -1, so it's 3D, and then counting the squares to get to cobalt is 7, so 3D7. So I'm going to do the electron configuration notation first. You still start at 1s. You always start at 1s. And you just start counting squares. So there's 2 squares in 1s. Then you move on to 2s. There's 2 squares there, so it's 2s2. And then 2p is 6. 3s is 2. 3p, 6. Then you move on to 4s, 2. And then after 4s is your 3d. So this is the last thing that goes in there. So 3d7. Sorry. And if you wanted to know valence electrons on this, again, you identify your highest S, which is 4s. And then you would just count how many valence electrons you have. If you had a 4p, then those would get added in here, but you don't, so they don't. This 3d does not count as a valence electron, because it is actually shielded by the 4s. Don't worry about what shielding is. We'll get to that later. So this would have 2 valence electrons. And then we can't actually figure out how many unpaired electrons it has until we do the orbital notation. Those numbers came from 1s2, there's 2 blocks in 1s. 2s2, here's your 2 blocks. Remember this, there's a line. Whoa, that was not a straight line. There's a line there. And then 2p is 1, 2, 3, 4, 5, 6. Just counting the squares in the periodic table, so 2p6. 3s2, 3p6. 4s2, and then we move on to 3d. And remember, there's 10 elements in a row on 3d, so it's 3d 10. 4p6, 5s2, and then 4d10, and so on and so forth. So coming back, we're doing cobalt, the orbital notation. So real quick, I'm just going to write the electron configuration notation for cobalt so we have that. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. So now we're going to draw the orbital notation. That's the one that kind of looks like a hangman game. So we have 1s, 2s, 2p, 3s, 3p, 4s. Oh, I gotta do that blank a little big. And then D has 5 blanks. So 1, 2, 3, 4, 5. 3D. Now we fill in our arrows. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And the only reason I draw these little half arrows is because they save time. Now D, remember, only gets 7. So 1, 2, 3, 4, 5, 6, 7. I'm really sorry about the coughing. I hope I'm not coming down with something. But so we already said that this has 2 valence electrons because this is our highest est and we don't have a matching p. Then the other question would be, how many unpaired electrons do we have? Well, here's your unpairs right here. You have 3 unpaired electrons. And like I said before, I'll explain the importance of the unpaired electrons later. Right now, we're just getting the what. We'll get the how and the why and all that later. The one thing I did say I was going to explain is why 3D is not a valence electron. There are exceptions where 3D or D electrons in general can be valence electrons, but most of the time your valence electrons are only the outermost energy level. You got to remember, this is energy level 4, this is energy level 3. So technically these electrons are outside these electrons, which makes these valence, because valence means the outermost electrons, the electrons that are capable of participating in bonding. So D's and F's, at this level, we're not going to count them as valence electrons. And then, let's do we need to do a P block. So let's do, how about oxygen? That one's a good one. All right, so oxygen has 8 electrons, and it is in 2p, and it's the 4th element in 2p. So let's do the orbital notation first. So you start with 1s, then 2s, and then 2p, and that's as far as we have to go. So you start filling in 1, 2, 3, 4, and then we only need to do 4 in this 2p, so 1, 2, 3, 4. And from here we can say that valence electrons find your highest s, which in this case is 2s, and is there a matching p? In this case there finally is. 2s is our highest, so that means the 2p goes with it. So oxygen has 1, 2, 3, 4, 5, 6 valence electrons, but only 2 unpairs. And then if we were to write the electron configuration notation, we would say 1s2, 2s2, 2p4. And that's literally all there is to it. Now, there is a shortcut that you can do for really big elements. And that's the noble gas notation. And so the way that this works, you can pause this and write this down, is you take a big element, let's say like gold. Seems to be very popular today. Gold is in row 6. It is in the D block, so that means it is 5D, and it is the 9th element in that row, so 5D9. And to do the noble gas, all you do is backtrack to the last noble gas that you went through. So since gold is on row 6, we're going to be looking for the noble gas at the end of row 5, which is xenon. So you would just write xenon, and it takes care of all the stuff before that, and you just pick up after xenon. So what's after xenon? 6s. So you would do 6s2, and then after 6s is 4f14, and then you're 5d, so 5d9. And if the question then asks, how many unpaired electrons does it have? Well, you know that the 4f is full, you know the 6s is full, so those are not going to be unpaired electrons. You only have 5d, so you would just draw d. 1, 2, 3, 4, 5, 5d, and then fill it in with the 9 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. So how many unpaired electrons? 1. How many valence electrons? Right here. You have 6s2. This is your highest s, so you would have 2 valence electrons. And that, ladies and gents, is the end of my show.